Hello, Stats class. This is the first of the Chapter 11 pre-response questions from 2003 Form B number 5. And it has some probability mixed in, so we're actually going to do a little bit of Chapter 5 here, and Chapter 6 for Part B, and then Chapter 11 comes in on Part C. And that's getting to be more and more common in the more recent years to have mixed questions like this. So we'll make sure we do some for sure in the next week if we have, besides what we've already done. So the probability, I'm going to skip over the rules of the game. I'll let you read those on your own, but let's start with this first one, which is pretty easy. The probability that you will get a number, not a skunk means you lose, on all three of the first spins. So as you can see, there's 3/4 chance of getting a number, 3/4 chance of getting a prize, and we want to do that 3 times in a row, so that's just to the third. And if you type that in your calculator, it's 0.421875. You're welcome to round that off. It's about 42% chance of getting 3 prizes in a row, basically. And then the next question is about expected value, which is a Chapter 6 topic. Let's say we already have won $800, and the next spin that we're about to do could be a skunk, which means we would lose that 800 we already won, or it could be one of these, and then it would just get added on to what we already have. So the expected value, remember, is the sum of all the possible values times their probabilities. So I'm going to just think through each one of these 4 sections of the wheel and say, okay, if I get a skunk, that means that I win nothing. So that's the first value times the probability if that is a 4th. If I spin 100, then I win, technically I win 900 because I have the 800 I already won plus that extra 100. So there's a 1/4 chance that I'll walk away with $900. If I spin the 200, then I have the 800 plus the 200, it would be $1,000. Or if I spin the 500, I get to keep the 800 I already have, plus I get 500 more, which is 1,300. Now it's possible to also think about this as here I lose 800, so you could try doing like a negative 800 and a 100 and a 200 and a 500. If you do that, then at the end you have to add that 800 that you already had. So I like it better this way because that doesn't have that extra step. And you end up with an $800 total. The expected value is 800. In other words, the amount I already have is the same as what I would expect to get if I did this scenario over and over. So you could try it that other way if you want to, where you think about the negative and just the small amounts without the 800 added in already. If you do that, you have to add 800 at the end. And then here's the Chapter 11 part. Somebody's complaining and saying, I don't think this wheel is fair. I feel like people are getting skunks more often than they should. And we want to know how can we tell if these are equally likely or not? So these, I just realized that's supposed to be a $, not an S. Sorry. I'm seeing with this one. Take those. These are observed values. And the expected value that we would expect to find, if I spun 100 times and they were all equally likely, I'd expect to get 25 each time. Well, now that's kind of sounding like a chi-square test, isn't it? So this is where the Chapter 11 comes in. Appropriate statistical evidence, remember, means do all 4 steps. So I'm going to do them, but I'm going to do them kind of faster than usual. I'm going to, go through I'm going to slow down when I get to the important part, which is the calculations. So state would be, well, first I got to figure out which type of test this is. What kind of test is it where we have a list of expected counts compared to observed counts? That's chi-squared goodness of fit. And so my null hypothesis is that the 4 sections are equally likely, or 4 outcomes. The formal wording of that would be the proportion of each section matches what we expect it to, which means that they're equally likely is a good way of saying that. All the proportions are the same is basically our null. Alternate is the proportions are not all the same. At least one proportion is different. And make sure you have not written your alternate and null hypothesis about the sample. I don't want to say observed counts are the same as expected counts because that's the sample. I want to say the proportions or the outcomes themselves. I want to talk about the population as if I'm spinning this infinitely many times. Plan, and then I'm going to do do and conclude over here because it doesn't seem like it's going to fit on my page otherwise. So plan is tell what kind of test it is. It's a chi-square homogeneity test. No, it's not homogeneity, it's goodness of fit. Goodness of fit because we have a hypothesized set of proportions, 25% each. And so I'm going to do random. Yes, we're spinning a wheel, and that would be a random sample. Remember, in chi-square land, we don't have a normal condition anymore. We have a large enough count condition. And we check our expected counts to see if they're all bigger than 5. Oh, look, they are. They're all 25. So this is a yes because all E's are 25, which is greater than 5. Independent, yes, because first of all, spinning a wheel is independent each time it spins, but also because 100 spins is less than 10% of all possible spins. You could say it either way. The do is the part I want to make sure I talk about because this you could do it on your calculator, and I'll show you that in a minute, but what you really should do in addition to that is write out the chi-square formula. So remember, we're adding a bunch of things together, and the things we're adding are observed minus expected. Maybe I'll write that first. Observed minus expected squared over expected. We're going to do that 4 times and add them together. So I will show that I know the formula by writing the first few out. 33 minus 25 is the first one. Square it and divide by 25. Do it again with the 21 minus 25. You could write out all 4 and it really wouldn't be too much trouble on this problem. But on the AP test, they like you to write out at least 2 of them. I like that too, actually, not just the AP people. So write out at least 2 of them and then do a ... and let your calculator do the rest if you want to. So here's how it looks on the calculator. In your stat edit, you would put in your observed counts in list 1, your expected counts in list 2. If you have the shortcut, that's in stat tests, and towards the bottom, GOF tests. But if you don't have the shortcut, remember you can always go to list 3 and the very top and tell it to do basically this formula. So this is what you would be doing if you don't have that extra shortcut. You'd be telling it to do list 1 minus list 2 squared divided by list 2, and then you would find the sum of this list to be your chi-square value. But if you do it with the test, it does that part for you, which is kind of nice. Tell it which list to look in. DF is categories minus 1, so 4 minus 1 is 3, and calculate. And here's what I got. I got chi-squared is 4.24, which also would be the sum of that list if you did it that way. P, if you did it the long way, it would be chi-square CDF of 4.24 and 999 and DF of 3. And it ought to come out the same as what the calculator says, which is 0.2367, something like that. About 23% chance. This is not significant. It's less than, or it's greater than 0.05. That's my conclude stage. Since P is 0.2367, it's greater than 0.05. I forgot to say alpha is 0.05 over here. It's okay if you forget and go back to it later. Nobody will know, right? We do not reject the null that the 4 outcomes are equally likely. I'll just spin it. And this customer has nothing to complain about. They're just being grumpy. All right, so that is it for that question.